Okay, so again, I still haven't posted the notes because I'm still fiddling with them. To be honest, so today we're going to do, again, we're going to do, I blitzed through in the final 5 minutes the start of this in last lecture, but I just want to do a better job of it this time and get to the Unruh effect. Now, I was going to, I had in my mind that the Unruh effect was going to be the simplest. It's both kind of an important and in some sense simple application of quantum field theory and curved spacetime. On the other hand, as I was actually writing up the notes in detail, I realized there's one integral which actually is kind of disgusting to do. So I don't really want to do it on the board, and I don't really want to. Anyway, I forgot about this, and so it's actually not. In principle, it's a simple thing. In practice, it turns out to be a little bit more complicated than I had hoped. And so, I'm going to basically set it up and show you the integral that you would have to do to get the result. And then, unfortunately, we're not going to do it. Or at least we're not going to do it in class. I'm still wondering about whether to maybe make it one of the homework assignments. But in any case, we'll at least hopefully get the essential idea. Okay, so let's just start. Let's just to all be on the same page. Let's just quickly do a 1-minute review of quantum mechanics. Then we'll do a 5-minute review of quantum field theory in flat space-time, and by then we'll be ready to do quantum field theory in curved space-time. And then as our first application, we'll do the Unruh effect, modulo the integral that we actually want to. Okay, so quantum mechanics, Dirac told us to do the following. He gives you a Lagrangian to start with, some function of the position, or the variables q and their time derivatives. And to quantize this thing, you are instructed to find the momentum conjugate to q by differentiating the Lagrangian with respect to q dot. And then you define, the Hamiltonian from this thing. This is now a function of p and q. So now this guy is an operator, and it's the thing that you use to evolve the wave function of the system. The Hamiltonian acts as the generator of time evolution in the Schrodinger equation. Okay, so as long as we restrict our attention to free fields, which we fortunately can do in both the black hole case and the two sort of killer applications of quantum field theory and curved spacetime, as long as we restrict ourselves to Lagrangians that are quadratic in the fields, there's not much more to quantum field theory than an application of this technology to mode by mode in Fourier space. So actually, let me just say one more thing here. So in particular, the simplest Lagrangian to which we apply this whole business is the harmonic oscillator. So the harmonic oscillator is a system for which we end up with a Hamiltonian that's quadratic in the momentum and also quadratic in the position variable, configuration variable q. And just remember that, so we quantize this thing by imposing Dirac's canonical commutation relations, that the q's all commute with the q's and the p's all commute with the p's, but the q's and p's do not commute. And so Dirac, also noticed that that applied to this Hamiltonian, a clever approach to applying these rules to this guy is to define the new operator A, which is this linear combination, and to notice that these commutation relations applied to this operator implies that it satisfies that, and let's say there's a bunch of Q's and a bunch of P's, then this would just be A sub I combines Qi and its conjugate P sub I. That all of the A's commute with each other, and that all of the A daggers commute with each other, but that A does not commute with A dagger. And then, if you rewrite the Hamiltonian in terms of these guys, it looks like this. And the eigenstates of the Hamiltonian are, well, the lowest eigenstate, 0. The ground state is the state that is annihilated by any of the so-called annihilation operators A. And then all of the other eigenstates of the system are obtained by acting on this with just a bunch of creation operators. As many different creation operators as we want, as many different times as we want. Okay. So now if we create such a state, so let's say, for example, let's say that I took n copies of this one creation operator A sub I, applied it to the ground state, and so I got a state here that I called n sub I. If I wanted to but suppose you hand me that state, and I don't know how it was created. I want to find out how many particles are in it. Well, there's an observable I can apply to it, the number operator. If I want to find out how many particles of type I are in the state, there's this number operator, direct notice, I can apply to it, this Hermitian operator. I apply it to any state, and the eigenvalue that it gives back is exactly the number of excitations n sub I in that state. Okay, so that was fast, but hopefully that rings a bell from a quantum mechanics course you've taken. Really, hopefully you've had to do this like 8 times in your life. That's the way it should be. Somehow the harmonic oscillator got to do more than once, but here we're just going to blitz through it as motivation for. So now in the case of quantum field theory, we just make everything continuous, but it's basically the same story. So in flat space, we'll look at the simplest Lagrangian we can think of again. So that's a real scalar field. So it has a kinetic term like this, and a potential term like this. So again, we quantize it just following Dirac. We calculate instead of P. So now phi is the analog of Q, and we want to calculate the momentum conjugate to phi. So that's going to be, we'll call it pi now, and that's the derivative with respect to, instead of Q dot, we take the derivative with respect to phi dot. So in this case, that'll just be phi dot. And then instead of these commutation relations, we give the continuum version. So now the Q's all commuted with the Q's. So here we take the phi at position x commutes with phi at any other position x prime. And similarly for all the p's commute with all the p's, and so we take the phi's at position x commute with the pi's at any other position x prime. And the q does not commute with p, and so here that becomes that phi at position x does not commute with pi at position x prime, well, it does commute with it, except when x is equal to x prime, in which case it does not commute with it. So that's expressed by just putting a delta function on the right-hand side. And then again, it was Dirac. Dirac did everything, basically. Did you guys know this thing about Dirac while we're talking about? I have a soft spot for talking about old, long ago physicists, and just what, in short summary, a great thing about Dirac is that so everything from the early days of quantum mechanics, they all have different names associated to them, like Heisenberg and Wigner and Schrödinger. It's not too much of an overstatement to say that actually 80% of that stuff was actually Dirac. But he would discover something, and then he was very generous about naming it after other people before it could be named after him. So he would, every time he discovered something, he would give it a name to give a name to one of his sort of compatriots. Anyway, Dirac was a real beast. He was awesome. But okay, so he noticed that since this is just very analogous to the quantum mechanic, to the harmonic oscillator, which he had previously solved this way, so he just noticed that if you went to Fourier space, then all the different Fourier space, if you just focused on a single Fourier mode K, the Lagrangian literally looked exactly like the harmonic oscillator Lagrangian with, and so in particular, if you if you go to Fourier space, so you expand the field in terms of So if you just take the field and expand it in terms of the Fourier mode solutions of the wave equation, so I should just say so you vary this guy with respect to phi. You take ds d phi, and the classical equation of motion is that thing is supposed to be equal to 0. So if you just do that in this Lagrangian, then you find that this equation of motion is nothing but minus box phi plus m squared phi is equal to 0, where box is this is getting too crowded. Okay, I'm going to redo this like a responsible lecturer in its own spot on the board. I once took, when I was in grad school, I took an intro string theory course from Ed Witten, and it was great. I didn't follow a lot of it, but one thing I would like to report is that I don't think he had lectured very many times before that as a grad course, or I don't know. I really don't know whether that's true or not. But the main thing that I want to say is that he writes very fast, okay, very fast on the board, and he fills up the board super fast, and then he just never erases it. He's just continually making a little circle for himself and writing something else in there. So by the end, it's just this incredible tapestry. And another important thing that he would do is he would always have chalk in this hand and eraser in this hand, and he would hold them very loosely, and he would gesticulate with his hands, and then sometimes the chalk or the eraser would just fly out of his hands, and so the chalk might, crash onto the floor, or the eraser might go flying over some of the audience's head and hit the wall or something like that. And the key thing is that he never really acknowledged it. He was just kind of still in the train of thought of the lecture, and so the chalk would just be thrown, and then he would just always just walk over and grab a new chalk or a new eraser and put, so his hands were full again. And he just never picked up the old eraser. It was always just, there were always 5 erasers on the ground by the end of class. Anyway, okay. That's neither here nor there. So I should have said, oh, that could serve in place of a joke today, potentially, since that was a completely irrelevant aside and a waste of everybody's time, much like the jokes usually are. So, so let's do that. So to continue, if we take the classical equation of motion for S, again, if you just vary d phi in that action and integrate the kinetic term once by parts to get to, so you can pull the factor of d phi, an overall factor of d phi outside, and look at what is left. The thing that is left has to vanish according to this equation, and it's minus box phi plus m squared phi equals 0, the flat space Klein-Gordon equation. So this box is just the flat space wave operator. And again, the solutions of this are just there are positive frequency solutions, e to the I k dot x minus omega t, where so I'll call these positive k solutions phi sub k, where omega is here I mean the positive square root of k squared plus m squared. Okay, so that's one solution, but then there are independent solutions, linearly independent solutions of negative frequency. Okay, and again, what I mean by positive frequency and negative frequency is the same as what you mean by positive energy or negative energy solutions of the Schrodinger equation. I mean that if I sit at a given point, at a fixed point x, and look how the complex number at my point in space changes in time, if it goes around in the complex plane in this direction, I call that positive frequency. In other words, if it goes like e to the minus I omega t, where omega is a positive number, I call that positive frequency. If it goes around in this direction, I call that negative frequency. So these are positive frequency. These are negative frequency. So together, these guys form a complete set of complete basis for the set of solutions to this equation. So Dirac says, well, you take the field phi, you expand it in terms of these solutions. And then the nice thing is that once you've done that, imposing those equal time commutation relations. So just like in the quantum mechanics case, imposing the canonical commutation relations in terms of the Q's and P's was exactly identical, equivalent to imposing those creation and annihilation operator commutation relations in terms of the A's and A daggers. Similarly, imposing those, in the continuum case, imposing those equal time commutation relations for the phi's and the pi's is equivalent to imposing the continuum analog of the creation and annihilation operator commutation relations above, that A at any k commutes with A at any other k prime, and that A dagger at any k commutes with any A dagger at any k prime, but that A sub k and A sub k prime dagger don't commute. And again, there is a natural state of no particles in it, which is the one that's annihilated by, since Dirac had already worked out the representation theory of this algebra for a single A, and now all this is saying, all these annihilation operators are saying is that for a single fixed k, if you look at two different k's, the annihilation operators just don't talk to each other. They all commute with one another. But if you look at where k is equal to k prime, if you focus on a single k, they just obey exactly the same algebra as the finite dimensional quantum mechanical creation annihilation operators. So he's already worked out the representation theory, and the ground state of the system is the one, the no particle state of the system is the one that's annihilated by every a sub k, every annihilation operator. And then you can create, you can create particles as you wish. So for example, if you want to create n particles of momentum k, you do that by just applying the annihilation operator, the creation operator, n sub k times to the vacuum. And now if you're handed a state and you want to measure how many particles are in the state of momentum k, you use the number operator appropriate to that momentum. You apply it to the state, the eigenvalue you get back is the answer you wanted. Okay, so that's it. That's all of quantum field theory in flat space-time. I don't know what you guys spent the rest of your quantum field theory course learning, but it was, anyway. So I may have ignored interactions here, and there may be like a little bit of extra detail that comes when you include non-quadratic terms in the Lagrangian, but for our purposes, this is all of quantum field theory in curved space-time. Dirac completely solved it. So now what happens when you go to curved space-time? Well, so, we just have to generalize the action. So we just have to put a root g in our expression for S up there and change eta mu nu to the general metric g mu nu. We vary, as we did before. We get the same wave equation we did before, minus box phi plus m squared phi is equal to 0, except that now box is the curved space Dirac operator, g mu nu, covariant derivative sub mu, covariant derivative sub nu. But other than that, the game is still exactly the same. We expand our field in terms of a complete set of orthonormal solutions, positive frequency and negative frequency solutions with coefficients, and we quantize by promoting the coefficients to operators that satisfy the same algebra of creation and annihilation operators. But again, the key point is that in curved space-time, so everything is proceeding exactly as it was before, and indeed we might go through the whole process and think nothing essential was different, except what did I do wrong? Oh. Except that in curved space, different observers, that is to say, two different people living at different places on the manifold, or maybe two people at the same point on the manifold, but one in two different states of motion, let's say, will disagree about how to split up the modes into positive and negative frequency parts. Okay, so let's first see why this never arises in flat space. In flat space, again, we said that the solutions of the wave equation are e to the I k vector dot x minus omega t. Those are the positive frequency solutions where omega is positive. It's the positive square root of k squared plus m squared. Okay, so the basic point is that suppose according to one inertial observer, this is a positive frequency solution. What will another inertial observer flying by at a different velocity think? He'll have some different coordinates on the space-time. Instead of the first guy's coordinates x prime and t prime, the person flying by will have coordinates x and t, or vice versa. I said that backwards, but so in terms of the new coordinates, well, what will this function look like for him? Well, it'll just be related by the k and omega are the components of a 4 vector. And so the same Lorentz transformation that relates the coordinates x and t to the coordinates x prime and t prime will convert this k vector to a new 4-vector k prime with new frequency omega prime and k prime. So he will describe that exact same mode as k prime dot x prime minus omega prime t prime. He'll describe it in his new coordinates. But the key point is just that for a Lorentz transformation relating two observers that are both moving forward in time, if omega was here, if omega was positive here, and k squared was less than omega squared, which it is if the thing has positive mass, then omega prime will also be positive. It takes a positive omega to a positive omega. Lorentz transformation does. So this guy will still describe this as a positive frequency mode. So there's none of the funny business in flat space. If you just talk about flat space and inertial observers like you normally do in quantum field theory, the following ambiguity doesn't arise. But as we'll see, especially tomorrow, really tomorrow will all be about the cosmological application of this. But in cosmology, for example, the universe expands. In general, observers at early times will disagree with observers at late times about how to split up the solution of the wave equation into positive and negative frequency modes. And so suppose they do. So suppose that we have our field and observer 1. Okay, let me just, for simplicity, instead of always writing down my integrals and so forth, let me, especially since in some cases Fourier expanding is not the most appropriate way to break up the solutions of the equation. So let me just schematically say so one observer will break up his field into a sum of positive and negative frequency solutions of the wave equation. So he'll call his solutions phi n and phi n star. But some other person will come along and he'll say, no, we should break it up this way in terms of according to me, the mode functions should be split up differently. The positive frequency mode functions are phi bar, and the negative frequency mode functions are phi bar star. And this guy calls the coefficients A and A dagger. This one calls the Fourier coefficients A bar and A bar dagger. Okay, but now suppose that what this observer calls phi n, what he calls negative frequency is actually is not a purely negative frequency according to the other guy. Suppose it's some linear combination alpha sub n, some coefficient alpha sub n times his negative frequency mode plus some other coefficient beta sub n times his positive frequency mode. Okay, so suppose this guy's negative frequency mode has some admixture of what the other guy calls positive frequency. You know what I mean? Do you know what I mean? I have a feeling that for a few minutes now, whenever I meant positive frequency, I've been saying negative frequency. But the main point I want to say is that they disagree. Suppose that this guy's positive frequency mode includes some admixture of what the other guy calls negative frequency. Well, let's just plug it in here. If we just plug that expression into this expansion, Okay, I'm just substituting phi n bar here, and the complex conjugate of that expression here. Now we just collect the coefficients of phi n and phi n bar. So we have two, phi n appears twice here and here. So its coefficients are alpha n bar plus beta n star n bar dagger. And then there's a corresponding coefficient. I won't write it out explicitly if we collect the terms proportional to phi n star. Okay? So if we just compare this expression to this expression, we see that these two expressions are equal. These were just two different ways to expand what is ultimately physically the same field operator. So this guy's annihilation operator, A sub n, is equal to this. Just these two coefficients of this mode have to be equal to one another. So A sub n is equal to alpha sub n bar plus beta sub n star bar dagger. Okay, so one guy's annihilation operator is an admixture of the other guy's annihilation and creation operators. Okay, so what's such a big deal about that? Well, so the unbarred guy will define, let's say the unbarred guy is Dirac. Yeah.
Why is it that in general I expect phi n bar to be made up of phi n? Wouldn't I expect it to be a sum of a whole bunch of different phi n's in
Indeed,
general?
you would. You absolutely. That's absolutely correct. I'm just for simplicity have suppressed that. So you're absolutely right that in general, phi n bar will be some general. It's a general function. It's going to be some complete sum over the basis of the other guy. So it's going to be a sum over m of alpha nm phi m plus beta nm phi m star, like that. General expression should be like that, and you can go through and do the same. Go through and do the same business. And just to avoid algebraic clutter, I'm assuming that the simplest thing happens, which is that a mode gets mixed into just one mode and its corresponding complex conjugate. In cosmology, that is exactly what happens. If you focus on a given spatial Fourier mode K, the spatial translational invariance of the universe demands that at linear level, modes of different K just don't talk to each other. They just all evolve independently of one another. And so this is exactly what happens in cosmology, that if this n is the spatial wave vector K, then yeah, the Fourier mode, then this is exactly the formula you get. There's no mixing. But yeah, good point. So the unbarred guy, he defines his vacuum state 0 by the condition that it's annihilated by all of his annihilation operators. Okay, and his number operator, the operator that he uses to evaluate how many particles of type n are in a given state that you hand to him, his operator is observable that he defines as this guy. But the other guy is not intimidated by the fact that the first guy was Dirac. I mean, the other guy is Dirac bar or something like that. He's just an early universe. He was so long ago he didn't know how awesome Dirac was, so he didn't even know yet to be intimidated by Dirac. So he was like, no, I have an equally valid opinion about what the vacuum state is. So he defines it to be 0 bar, the thing that's annihilated by his A bars. And he defines his annihilation operator n bar to be built from his creation annihilation operators, A bar and n bar. Okay, but so now, the point is, what happens if we now apply, this guy's number operator to the other guy's vacuum state? So let's say this is us. We're the late time observer. We are Dirac for the purposes of this discussion. So this is us today. We use our number operator, but the universe started out in the vacuum state according to the early observer. Okay, kind of a natural supposition. So the universe started out in the state 0 bar, and now we want to know what is the expectation value, what is the number of particles in this state, according to us. According to us, what is the expectation value of the number of particles in that state, which was the vacuum state according to the early time observer? According to the early time observer, if we put an n bar here and calculated this would be 0. The early time observer would say his state has 0 particles in it. But what do we say? Well, if we just plug in this formula here, we say that it's alpha n star n bar dagger plus beta n star plus beta n not star n bar. So in other words, I'm plugging in n is equal to an dagger an. So first I'm plugging in the dagger of this expression. Now I just plug in that expression itself. Okay, but now we can. So now we have 2 terms times 2 terms. So there's 4 terms here, but 3 of them vanish. So any term where this annihilation operator acts on this guy vanishes, and any term where this dagger of an annihilation operator acts on this dagger of the vacuum state vanishes. So the only non-vanishing term comes from this guy times this guy. Okay, so this is equal to beta n absolute value squared 0 a bar n dagger. And then this thing is 1. So if you just imagine you use the commutation relation for. Imagine you use this commutation relation, a bar n dagger is equal to 1 to permute that guy. So you permute it, and you get 1 plus the number operator. The number operator n bar gets killed by the state 0. So you're just left with the 1. Okay. Okay, so this is an important result worth remembering. That this is like the. It's very simple, but it's like the key result in quantum field theory and curved spacetime. So it's one of the 2 key results. That this sort of transformation, which also happens, you may have met it in Kant's matter. But anyway, this sort of transformation where one person's annihilation operator is a mixture of the other person's annihilation and creation operators is called the so-called Bogoliubov transformation. This coefficient is these are the Bogoliubov alpha coefficients and the Bogoliubov beta coefficients. And the point is that the number of the expectation value of the number of particles in one guy's vacuum according to the other guy is proportional to the absolute value squared of the Bogoliubov beta coefficients. Okay, so that's kind of the general result, and now we just want to apply that to the Unruh effect. Okay, so the Unruh effect is kind of the primordial example of this because it's all just in flat space. There's no curved space in the game. The only thing is that we'll just look at two different coordinatizations of flat space. So let's just look at two-dimensional flat space. So we have one spatial coordinate x, one time coordinate t. These are the coordinates that you and I would normally use, the normal Cartesian coordinates, in terms of which the metric looks like minus dt squared plus dx squared. So we want to ultimately get into the reference, we want to ultimately change to coordinates that are appropriate to a uniformly accelerating observer. The uniformly accelerating observer moves along a hyperbola here that asymptotes to the light cone. And so we, who use this coordinate t, we will have one opinion about what negative frequency means. In other words, what positive frequency means. So what positive frequency means for us is we sit at a fixed point in space in our coordinates x, and we ask, how does the complex number at our point in space oscillate which direction does it go in the complex plane? But then, so let's say we're sitting here, we're moving along, we're sitting at a fixed position in space and asking that question. But then this other guy with a rocket, with his rocket turned on, goes zooming by. Locally, he passes right next to us, and he asks the same question. And the question is, to what extent does he disagree with us? To some extent, he's going to regard what we call a purely positive frequency thing as a linear combination of positive and negative frequency. So first, we just need to get into his coordinates. So it's kind of helpful to do this. It's a little bit unilluminating if you do it in just one step. So it's good to do it in a couple of steps here. So really 4 steps. So the 4 steps will be, we'll start in Cartesian coordinates. We'll switch to ordinary light cone coordinates, u plus and u minus. Then we'll warp those light coordinates. So we'll just take this coordinate and we'll kind of warp it into a new guy which we'll call u bar plus, and a new guy which we'll call u bar minus. And then we'll go from those warped, we'll imagine that those warped light cone coordinates, we'll just treat them as if they were ordinary light cone coordinates and go back to what would be the corresponding Cartesian coordinates. We'll just invert the transformation. So in other words, let's start. So step 1, go to light cone coordinates. U plus and u minus are defined as x plus and minus t. So in other words, this is the u plus axis. U plus runs from negative infinity to positive infinity along this axis. U minus runs from negative infinity to positive infinity along this axis. So in terms of these coordinates, if we just take du plus minus, that's dx plus minus dt. So if we just substitute that in here, we find that the metric becomes, in those coordinates, it's just du plus du minus. Okay, now let's do the warping that I just described. So we'll introduce a constant parameter a, which will be inversely proportional to the acceleration. In fact, why did I call that a? If it's anyway, okay. So because it's too late now for me to. If I change my definition from a to 1 over a, I'm just going to start introducing algebra errors. But it does seem stupid now that I'm standing up here that the thing I called a is actually inversely proportional to the acceleration. That sounds like a notational error, but anyway, that's the way it is. So we'll define that to be a times our warped light cone coordinates, u bar plus and minus. So if we take the differential of this, we find that du plus minus is equal to e to the a u plus minus bar du plus minus bar. So in terms of these guys, if we just plug this into the metric, it becomes e to the a u plus bar plus u minus bar du plus bar du minus bar. In other words, it looks exactly the same as the previous as the metric did in the previous light cone coordinates, but with this warping factor in front. And then let's just go take this, do the exact analog of this transformation to go back to warped Cartesian coordinates. Okay, so we'll take the u bars and we'll convert from them to warped analogs of x and t. Okay, so if we just plug that in there, well, u bar plus u bar minus, you see it's just 2x bar. And du plus minus is equal to dx bar plus or minus dt bar. So if we plug that in there, just like we went from here to here, we're going to go from here to minus dt bar squared plus dx bar squared. Okay, so these, I called these warped Cartesian coordinates, these guys x bar and t bar. But normally these are called Rindler coordinates. And as they run from plus infinity to minus, as they run from minus infinity to plus infinity, they don't cover the whole of Minkowski space. If you think through the transformation, because here you can see as u plus minus runs from plus infinity to minus infinity, well, the exponential is always positive. So as u bar runs from minus infinity to infinity, u only runs from 0 to infinity. Okay, so we're parameterizing this positive quadrant in the u plus u minus plane. And that thing is called Rindler space. And what these coordinates look like, if you just plot the full transformation, is that the time coordinate, the t bar coordinate, here I'm drawing surfaces of constant t bar. Okay, they're just straight lines. So the bottom light cone here is t bar is equal to minus infinity, and then t bar is getting bigger and bigger. T bar is equal to 0, and then t bar is going up to plus infinity at the top light, along the top light cone. Meanwhile, x bar is constant. Are these hyperbole? Okay, the x bar equals constant surfaces are exactly, if you ride along a surface of x bar equals constant, you are a uniformly accelerated observer. This is the trajectory you would follow if you had a rocket that was boosting you with a constant force. You're firing it in that direction and being constantly accelerated in this direction. The hyperbole that come very close to the origin are people who have very strong rockets, very large acceleration. The people out here are people with very weak rockets. Very weak acceleration, but they're all asymptoting to the same light cone. Okay, so we want to see, we want to derive a basic result, which is that not only do these accelerated observers disagree with the inertial observers about what positive frequency is, but their disagreement has a very special form. The accelerated observers think that what the Minkowski observers call the ground state, the vacuum state, is actually a thermal state. So it's full of particles, not with any old distribution, but with exactly the Boltzmann distribution, with exactly the Bose-Einstein distribution. Okay. So to do that, let's just focus for simplicity on again, just a free scalar field. And now let's take it to be massless. It's going to simplify our life if we take it to be massless. So its field equation is this guy, where again, that's g mu nu, nabla mu, nabla nu. So the field equation, I should say, is that guy, where Fox is the flat space wave operator. So in Minkowski coordinates, this is d squared dt squared minus d squared dx squared acting on phi is equal to 0. Then if you work it out in these other coordinates, it turns out to be almost the same thing. It's d squared dt bar squared minus d squared dx bar squared. But there's an overall conformal factor in front, which I believe is, it's either e to the plus or minus 2a x bar. Oh, actually, do I have it here? I do, yeah, e to the minus is right. Okay, so, okay, but so this is just a conformal factor. So I mean, this is some non-zero quantity. So so if we just divide through by this, then phi happens to satisfy basically formally the identical equation in both coordinates. So according to this observer, he would say, oh, okay, the positive frequency solutions of this equation look like e to the I kx minus omega t. Okay, those are what he's going to call the positive frequency solutions phi sub k, where omega is equal to the absolute value of k. This guy will say, no. The solutions are actually e to the I kx bar minus omega t bar. Those are the positive frequency solutions, where again omega is equal to the absolute value of k. And so now, the only thing we need to do now is we're done. The only thing we need to do now is evaluate. We need to do the coordinate transformation to see how, if we rewrite these wave functions phi bar in terms of phi and phi star, what are the alpha coefficients and what are the beta coefficients? Okay, so we just want to do this expansion, this expansion here. And in fact, I should mention, I said before that for simplicity, we were going to look at the case where I neglected the sum and assumed that each negative frequency mode of one observer was just equal to a single sum of was just equal to a single negative frequency mode plus its complex conjugate. But again, the general case is actually this: that one guy's mode will have to be a general expansion over the complete basis of the other guy. Okay, so we want to just do that and calculate what is this beta coefficient, and then find that when we square it, that we get the Boltzmann distribution. So there's just one thing I need to tell you, one bit of formalism that I hadn't told you yet, about how to extract the beta coefficient. So suppose you know the mode functions in both, according to both observers, how do you actually calculate the beta coefficient formally? And the answer is, well, you define, we take first of all, we want our mode functions to be properly normalized. We want them to form an orthonormal set. So to do that, we need some normalization. Okay, may I beg just 5 more minutes? No, 2. You guys are driving too hard a bargain here. I need just one more minute, but I'm also willing to tell a joke to in return have a second minute. Okay, let's do that. So I like that we are discussing it though. A cow is trying to sort of climb up a tree, and bird flies overhead and is like, what are you doing? And the cow says, oh, I'm just climbing up to eat me some apples. And the bird says, that's actually just a maple tree, And the cow goes, no, I got him right here in my pocket. Anyway, okay, that's the whole brief. So what I wanted to say was the following. So there is a natural inner product that you can define between two solutions of the wave equation, or two functions, and it's this guy. So in flat space, it would be in curved space, we just have to appropriately make this thing covariant. So we, as usual, we replace the integration measure by, we have to insert a factor of root g to make the whole thing into a scalar. So this is the determinant of the 3 metric on the spatial slice that we're integrating over. And then the partial in the time direction, we're gonna express that by saying we have a unit time-like vector that points orthogonal to the 3-dimensional surface that we're integrating over, and that's what we differentiate with respect to. We take the directional derivative in that along that vector. Okay, so now even though we're in flat space, we actually want this. We want this formula because, well, depending on which coordinates we work in, we need, even though we're in flat space, we need the appropriately. We need a formula that works in any set of coordinates, which this guy does not. So, really, so these functions, these guys, if we plug them into this formula, both of them will find that the phi's and the phi stars form an orthonormal basis in the set if we add an appropriate prefactor. Okay, so the prefactor, for example, in this case will be I think if you just plug into that equation, the prefactor will just be 1 over square root 2 omega that you have to. So in other words, that exponential e to the I omega, e to the I kx minus omega t is not yet normalized. The normalization factor in front would be like this guy. Or yeah, it's possible. Or maybe there's also a 2 pi. Maybe there's also a square root of 2 pi cubed in here. Anyway, or 2 pi to the whatever spatial dimension in there. Yeah, sorry. This is the number of spatial dimensions here. So actually, in the Unruh case, we've just been using 1 spatial dimension, so this would just be dx. But this is just the appropriate integral over the purely spatial slice. Anyway, so you can convince yourself that if you do the expansion, if you do this expansion in terms of a phi plus a dagger phi star, where these guys are orthonormal, where the guys that you expand in are chosen to be an orthonormal set. You appropriately normalize them so that the phi n's and the phi m's have inner product delta mn. The corresponding stars, you'll see from that expression, will then have a minus sign, minus delta mn, and the phi's will be orthogonal to the phi stars. Positive frequency guys are orthogonal to the negative frequency guys. And similarly, you do that for the phi bars. So the phi bars are also normalized in exactly the same way. Then you can extract, if you know what the phi's are and you know what the phi bars are, you can extract the beta coefficient by simply evaluating the inner product between phi, a positive frequency phi, and a negative frequency phi bar. In other words, phi n inner producted with phi m bar star. So I take one guy's positive frequency mode inner producted with the other guy's negative frequency mode. That is exactly the coefficient beta nm. So now in practice, the problem is just that actually if you take, even though the solutions are very simple, the phi solution is very simple and the phi bar solution is very simple in the Unruh case, the fact that the coordinate transformation between them is not so simple. Just means that when you express them both in the same coordinates and try to do this integral, it actually is a little bit gross. So that's the thing which I had originally in my mind hoped to explicitly derive for you on the board, and I'm actually going to give up on doing that on the board. Although, well, yeah, I'll ask David, talk with David about whether maybe we should do it on the homework or maybe not. But in any case, in practice, you see it's a straightforward thing. You just take these two functions, normalize them appropriately using that integral. That's the easy part. Then you take their inner product, calculate beta, and then when you actually when you actually sum, when you actually calculate what is one guy's what is the square of beta n? So how many particles does the Rindler observer think are in state n? If the state is really what the what the ordinary inertial observer would call the vacuum, you find that it is e to the minus omega times some coefficient, which I will call t, minus 1. And I call it that because, sorry, you find that it's e to the minus omega times some coefficient, which I'll call 1 over t, minus 1. And I call it 1 over t because that is exactly the Bose-Einstein expression. You know, that's the thing we met in lecture 5 when we talked about thermodynamics. It's the famous expression for an ideal gas of bosons in thermal equilibrium. What's the expected occupation number of a given state of energy omega? It's omega over the temperature, e to the omega over the temperature. Sorry, and this should be a plus sign. But in any case, you get the point. Even if you never work it out yourself, you can see that conceptually speaking, everything is done. There's just one integral to be evaluated. And the claim is that if you evaluate the integral, as Unruh did back in the 70s, the answer for the square of beta is the Bose-Einstein distribution function. So in other words, an accelerating observer is predicted by GR to see a thermal bath of particles, and that turns out to be very closely related to Hawking's result that a black hole evaporates, that a black hole radiates, because if you compare two observers very close to the horizon of the black hole, okay, one of which is just an inertial observer falling right in, and the other of which is a guy using his rocket to sit at a steady height above the black hole. Well, in the limit that you're very close to the black hole, so you look at such a small region around the horizon that it's basically Minkowski space, those two observers, the infalling observer is exactly the analog of the Minkowski observer, who's just freely falling, moving along a geodesic, and the guy who's using his rocket to hover above the horizon is exactly one of these Rindler observers, moving along an accelerated trajectory. And so the fact that this guy observes radiation coming out of the black hole is exactly the same as the fact that the accelerated observer here observes radiation in the vacuum according to the Minkowski observer. Okay, and then I think that is all I'm going to say about that. Yeah. It's proportional to it. So the temperature you see is proportional to your proper acceleration. Sorry, sorry. This is where a is not the parameter that I used. Is not the parameter that I used. Oh, and there's a 2 pi. Sorry. So I think it's actually 2 pi a in units where we set k Boltzmann and h bar equal k Boltzmann, h bar, and g equal 1. Where a is the acceleration, not the parameter a over there. So it makes sense. The more accelerated you are, the hotter the effect is. So now the thing we'll derive tomorrow, which is much easier, is how the inflation is how during an early epoch of inflation, the scalar field that drove the inflation would also automatically have, even if it started in its vacuum state, it would automatically, the expansion would create particles by this same mechanism in that guy. And one way to phrase what's going on there is that the horizon in de Sitter space has a temperature exactly analogous to the temperature here. So I think maybe on either the homework or in the tutorial, maybe you'll derive the temperature of de Sitter space that way. But another way to derive it is the way that we'll do it in class. Well, is the way that we'll do it in class tomorrow. But ultimately, the key point is that physically they have the same effect. Okay, that's it. Sorry to run over. Yeah. Maybe before I answer that question, because I ran over. Yeah, sorry. Don't. In case we. Oh well. I just want to say. Don't feel obliged to stay any longer. Apologies for running over.
Sorry. To in principle get the coefficients out, I would think I would take the 5-bar expression, express x and t in terms of x and t, and then integrate with the exponential to pull out my coefficients. The way you, I'm just confused as to where this inner product definition comes from.
So let's see. Let's say you have. Let's forget about exactly what the inner product is. Let's say that you have an inner product, and such that the phi n's and the phi m's are normalized in this way that I said, are normalized like this, and the phi bars and the phi bar stars are normalized the same way. Then, without having the explicit expression here for the inner product, you can just you can derive this fact that the beta nm coefficient is the inner product of one with the other. Is that with the star of the other? Is that the part that is confusing?
No, I agree.
Or the question is, why is this the inner product that we're defining?
Yeah.